Record. Okay, so I'm not sure if you received a notification, but we are now recording. So what my plans are here, I'm going to pull up the practice test. I'll go through as many questions as I can from start to finish, and then please let me know if you have specific questions. You can save your questions till the end. I'll stop record, and then you can ask, or you can place them in the chat. All right, so our first question here. Let's see, on the practice test, we're asked about properties of a gas. So hopefully everybody can see this here. So this is really just the definition of a gas here that we're looking for. And we know that a gas will assume the shape and volume of its container. It will expand. It's very compressible, a gas in general, because there's so much space between the molecules, and the molecules themselves don't take up that much space to the total volume. They also form homogeneous mixtures with one another in any proportion. So you could have, 1 mole and 5 moles and vice versa. So the only one that is not a property would be E here, which lists the density as being much larger to those of a corresponding liquid. So if a gas condensed into a liquid, its density would be much higher than in its gaseous state. So we'll go with E for number one. Again, some of these are just going to be like definitions. A unit of pressure, or the definition of pressure, I'm sorry. So again, a definition, force divided by area is how we measure pressure. So all of our units that represent atmospheric pressure, remember they're measuring that force pushing down on us. Let's see. Question number 3 here. This is our first conversion. And notice you're given some conversion factors here. We are asked to determine our pressure in millimeters of mercury, so mmHg, and we're given atmospheres here. So we always start with what we're given. Those are supposed to be eights. Sorry, guys. Let me see if I can write a little harder here. 0.088 atmospheres. And then we're going to multiply by 760 on top here because this is our conversion factor. 1 torr is 1 millimeter mercury, so we know 760 torr is the same as, oh, those are supposed to be mmHgs. So we know that if we set up our conversion like this, our atmospheres will cancel, and then we multiply our 0.88 by 760, and we'll get our value in our new unit, millimeters of mercury. All right, so also feel free to raise a hand or stop me if I'm going at, too fast of a pace. But you're going to see some conversions. This next question, this is kind of the definition of a certain law that we studied here. So we're going to look at what's being related. We have pressure is inversely proportional to volume. So we looked at that, how if we multiply pressure times volume, we would get a constant. This is our definition of Boyle's law. And again, they are inversely proportional in the sense that if you increase pressure, you're squishing something, right? You're making it a smaller volume. So we see that inverse proportionality with Boyle's law for pressure and volume. And let's apply that actually in question 5 here. We have an ideal gas. We have its volume will be doubled. Temperature is constant. So we know that we're only going to be relating pressure to volume here. So out of our 3 variables, P1, V1 over T1, right? So we could set these equal to a second set of variables here, P2, V2 over T2. But since temperature is constant, we can eliminate that variable, and our combined gas law becomes a little more simplified, and we see that it's really just a Boyle's law relationship. So if I'm told that my initial pressure was 100 torr, and we can put whatever volume we want. So I'll say 100 torr times 1 liter here. My new pressure we're solved for, and we're told that the volume is doubled. So now my new equation here that I can set up would be 100, say, times 1 liter would equal 2 liters when we double that volume times our new pressure. So you can see if I rearrange this to solve for x, I will just divide by 2 here. So it's really 100 divided by 2. My new pressure would be 50 torr. So notice I used the same unit that we started with. That's because we're just doing this kind of like ratio, this relationship. So we're not actually utilizing the gas constant R here. So it's okay to keep units in torr if we're just looking at like this relationship between changing one variable versus the other, and we're keeping the same unit of torr for our final answer, then we can skip a conversion step. All right, so we'll move to the next page if I don't see any hands. All right, so now I have a gas. My sample has an initial pressure. So I'm going to mark that my P1 and a volume, my V1 here of, we have 0.987 atmospheres for pressure, and then we have 12.8 as our volume in liters. Oh, we got a pop-up box there. All right, so we want to know what our final pressure is. So we're solved for P2 if our V2 is now 25.6 liters. So let's see how we would set this up. We have atmospheres, we have liters, so our units look good. Let's see if we can set up a P1 V1 equals P2 V2 scenario here. And then we're going to solve for our P2. So we know that we would have to divide P1 V1 by V2 to get P2 by itself. So this would look like 0.987. All right, let's see if I can maybe write it down here. 0.987 ATM. Oh, you know what, guys? I think I might go to a whiteboard for this one. So let me stop share this screen, and then I'm going to pull the values in from problem 6 to the whiteboard because it's at least a little easier to write on. All right, so if you were following along our pressure 1, once the whiteboard loads here, there we go. So P1 was given as this 0.987 ATM. And we had our V1 was 12.8 liters. And then our V2 was given as 25.6 liters. Okay. All right. So we know P1, V1 over V2 will give us our P2. All right. So let's plug in. We're going to have 0.987. We'll multiply that in atmospheres by our volume 1, 12.8 liters. And then we divide by our new volume. So we have a larger volume here. So we expect our pressure would be less, right? So we plug in these values, that 0.987 times 12.8 divided by 25, and we should get a lower pressure, which is 0.494 if we keep 3 sig figs. And this is what we would see on our answers. Let's go back here. Let me close the whiteboard. But it's the same setup that we've been using in the past, where we have P1, V1 over V2 to solve for P2. Yeah, it's getting a little messy here. So let's see, let me delete that and our answer choice E. All right, so again, plug in to our equation and solve for our new pressure or volume with the Boyle's law relationship. Let's see here. So now we have in number 7, we have some carbon dioxide gas. We have our initial temperature, our initial pressure, and an initial volume. So if we're asked to find our new pressure, if the volume is increased, this is our V2, and then it looks like temperature is actually kept constant. So this is again is just a Boyle's law relationship. So P1, V1, and then we'll divide by V2 to get our P2. So let's see if I can squeeze this off to the side here. So P1, V1. All right, let's let's go to another whiteboard real quick here. I will grab this information and I'll meet you on the whiteboard. Or actually, you know what? We've done a few Boyle's Law. So I'll skip this one in the video so we can keep moving and we'll come back to this if we have time. Um, so number 8 here, the Kelvin temperature at 24°C. So we know that we just add 273 to get that's supposed to be a 3, 273 to get our value in Kelvin. So this would be 297, 273 plus 24. Now, what is the temperature in Celsius at 4 Kelvin? So now we're going to take 4 minus 273. So we should get D again. So 269. So much more frequently will you be doing this conversion, but you should be able to do it both ways. Because we always need our unit of Kelvin for temperature when we plug into our ideal gas law equation. All right, so now we have a volume and temperature relationship. So we have our V1, we have our T1, and then, excuse me, this will be our T2 over here, the 220 degrees Celsius. And then we want to know our final volume. So this is our V1 over T1, Charles law relationship would equal V2 over T2. So what we can do is once we convert these to Kelvin, we could plug in and say that if I have 32.4 liters is my V1, my T1 will be 293 Kelvin, right? 273 plus 20 that was given. And then I want to solve for my V2 over here. So now I'm going to multiply both sides by T2. So that's going to be 493. All right, so we plug in 32.4 times 493, and then we're going to divide by 293. Sorry, we kind of lost what we're seeing here. Let's see here. So this is supposed to be 493 times 32.4 divided by 293. And we get for number 10, an increase in volume, right? Because we're heating our gas quite significantly. So it looks like we almost double that volume, right? All right, and remember that's a relationship between the Kelvin temperature. So it looks like we multiply 10 times the temperature, right? We have 20 degrees to 220. But when we relate them in Kelvin, it's only like a mere, not even a doubling. So number 10, we'll put answer choice D, and we'll look at the Charles law, right? Relationship there. Number 11, I have an initial volume, initial temperature. I want to know my new temperature at my new volume. And note, we always have to keep the other variables constant. So we see constant pressure here. Let's see if I can erase some of this here. Oop, where are we at? Nope, I don't know where my eraser is. Sorry, guys. So we'll just kind of work around this. Oh, let's see. There we go. There we go. I have a clear space now. All right. So we have V1, we have T1, and then we have V2. So same relationship, right? V1 over T1 equals V2. My stylist does not want to do twos for some reason. So let's plug in these numbers again with that Kelvin relationship and what temperature. So we're solving for T2 now in this scenario. So we can rearrange this equation to get to T2 being by itself. So what we can do is we could either flip this and put T2 on top, or we can just multiply and divide until we get T2 by itself. So in the end, we would see T2 would equal, what do we have? V2 T1 over, oh, sorry, V yeah, V2 times T1 over our V1 here should give us our T2. Or like I said, you could invert this, you could flip this, and then have T1 over V1 is T2 over V2. And then we'll still have that T2 turn out to be the same kind of equation here. Let me see. I didn't plug this one in, so let's make sure we get our right answer. So we have 2.4 liters for our V1. Then we're going to multiply by 293. That's going to be our temperature in Kelvin. And then let's divide by our 4.6 liters. And then we would end up with, let's see here, for number 11, we want to get our answer in Kelvin. So we should get, oh, I'm sorry, our answer in Celsius rather. So we should get something around 313 for this one here. All right, so for number 11, so again, it's the same relationship, V1 T1 over V2 T2. We just have to rearrange and solve for our T2. Let's see here. What are the conditions of STP? So this is just definition. We know that we're at 0 Celsius, 760 atmospheres. We would be at 273 Kelvin and 760 torr. That's the same as 760 atmospheres. So this guy right here, that satisfies both of our scenarios. This is wrong, right? This should be 1 atmosphere. This is wrong. It should be 273 Kelvin. So just make sure that both of your conditions are going to be at either 0 Celsius, right? 273 Kelvin, or 1 atmosphere, or whatever the comparable to 1 atmosphere would be. But if you're using the ideal gas law, remember we always need Kelvin and ATM. So
Uh, just a fast question about the practices. Are we able to complete it as many times as we want?
I believe I have the settings set up for infinite attempts, so you should be able to. If you notice that you cannot, you can send me a message. I might have to go in and adjust settings. But you should be able to see the answers at the end, and you should be able to take it an infinite amount of times.
Uh, okay, thank you.
You're welcome. Hmm. Okay, so here we have to use the ideal gas law equation. So we're given a mass of methane. We're given a temperature, we're given a pressure, and we want to solve for volume, right? So this is what we're solving for. So we know that PV equals nRT. So I would know this equation, write down this equation somewhere. We want to solve for volume. But first we have to find out how many moles we have to plug in here. But our new equation is going to be nRT over V. So once we have moles, we can plug this in. To find moles, to find N, I would take my mass of methane, 35.2 grams. And you will have a periodic table, but for those that don't have one handy, I'm going to add 12 plus 4 to get my molar mass for methane, right? 1 carbon for hydrogen. So that gives 16 approximately grams per mole. So when I go to plug in moles here, I'm going to have 35.2 divided by 16, so about 2.2 moles. So we have 2.2, and I know I'm not writing all my units, 0.08, 206. Oh, all right. Oh, sorry, something's happening. I think I clicked a button by accident here. Let me, oh, okay. Let me stop for a second here. Stuff's popping up. Um, Still up. All right. Uh, Sorry, guys. When I'm sharing, sometimes I can't get to all the screens that I need to get to exit out of things. There we go. Okay. All right. So we were plugging in. I'm just going to write the R value here, just the letter R. right? But we know that it's 0.08206 here. My mess. And then we know that we have 25C, so we actually have 298K, right? So I have my N, my R, which we know we will plug in 0.08206, my T, and then my pressure should be on the bottom. Oh, I wrote V again by accident. Sorry, guys. So this should be a P. We'll divide by 1 atmosphere. Well, I guess it wouldn't have mattered if we divided by P or not. We're still going to get 2.2 times 0.08206 and then times 298 on top. So I'm getting answer choice A here. So my volume of 35.2 grams of methane would be about 53.7 liters. All right, so we've seen Charles' law, we've seen Boyle's law, we've seen the ideal gas law. So all of these may appear at some time. This here, this next question, this deals with the property of mass of a gas, and the topic really is surrounding kinetic molecular theory and the fact that a gas either diffuses or effuses in proportion with its mass. So what that means is the higher molar mass of a gas, the slower rate, the slower speed, right? Lower speed, we'll say, of movement. Not so much its rate, but the lower speed. So which of these gases will effuse most rapidly? We're looking for the lightest gas. So you could quickly go through and say, all right, nitrogen is a diatomic, so that's 28, right? Because we have 2 times 14. So 28. Carbon monoxide, that's CO. So I have 12 plus 16, so that's also 28 grams per mole. Hydrogen chloride, this is just HCl gas. This would be 1 plus 35, so I don't know, like 36 point something. Ammonia, that's 14 plus 3, so 17. So far ammonia is the lightest. And oxygen would be 32, 2 times 16. So all you have to do is figure out the gaseous state, the molecular formula that would exist. So if you have a diatomic, just know that you have 2 of those atoms. Find the molar mass, and then in this case, whoever is the lightest will move the fastest. So ammonia gas would effuse most quickly. All right, so remember with the gas and effusion or diffusion, so whether they mix or whether they sneak out of a small hole, like a pinhole, diffusion and effusion just relate to molar mass. Um, all right, so we have number 15. When will nitrogen behave most like an ideal gas? So I mentioned in class that gases like high temperature, right? They have all that energy. When you're in gaseous state, you probably have higher temperature than when you're in your liquid or solid phase. So high temperature and low pressure, right? They like to spread out. They don't like to be contained. So A for this one. Yeah, so high temperature, low pressure. They behave least, or any ideal gas, or any gas rather, will behave less than ideal at the opposite, at low temperature and high pressure, right? They'll be squished and they'll be cold. They'll be less energized, these molecules. So you might want to know when they behave least like an ideal gas, maybe for an exam sometime. Okay. Let's see. Let me move to more intermolecular forces here because we've been talking about gases this whole time. Let's see here. So what are the attractive forces that hold particles together in the condensed phase? So this would be either liquid or solid phase. We have the intermolecular forces. So in general, we have the London dispersion forces. We have dipole-dipole, H bonding, right? So bonding. So any of those 3 are the intermolecular forces that hold particles together. The intramolecular forces inside the molecules, those would be like covalent bonds. So ionic bonds wouldn't apply, covalent bonds, because that's an intramolecular inside the molecule or inside the ionic compound. So what's the attractive force between polar? So remember dispersion forces, everybody has those, nonpolar, polar, everybody. Dipole, though, this is specific to polar molecules. Um, and then when we talk about ion dipole interactions, you would need an ionic compound or an ion rather, like sodium ion, and then a polar compound here. So 3 would not apply. 2 is specific to our polar molecules. Right, so that's why it's only number 2 because it's specific to the polar molecules. All right, so just 3 main intermolecular forces to think about. The hydrogen bonding, remember, is a special case of that dipole-dipole interaction when we have an extreme dipole between hydrogen and oxygen, nitrogen, or fluorine. So I'll write that down real quick here because this question, we're asked about hydrogen sulfide. So we want to double check and make sure we don't have any of these hydrogen bondings possible. So we have sulfur in the middle, right? If I drew my Lewis structure for hydrogen sulfide, oh, those are my lone pairs, it will look something like this. So I know I have London dispersion, but I'm looking for the strongest. So I'll set this off to the side because I know it's there. Disulfide linkages. We didn't talk about these, but these are sometimes in DNA or polymers and things. Sulfur can link with other sulfur atoms, but we didn't talk about those, so I would guess that that's not going to be the right answer because that's beyond what we talked about in class. Is there an ion? No, so I'm going to say no ion dipole. Dipole forces. Well, I see a dipole in the direction of sulfur. So I'm going to grab this here as my answer because I know it's stronger than London dispersion forces, these dipole-dipole interactions. And I know that I can't hydrogen bond because I don't have any of these OH, NH, or FH bonds in my molecule. All right, so again, look for the strongest intermolecular force. If it can hydrogen bond, it's going to be hydrogen bonding. The next strongest would be dipole-dipole, and then all molecules, polar, nonpolar, have the London dispersion. All right, number 21 here. Which of these can form hydrogen bonds with water molecules? Okay, so let's work through here. So number 1, we have a sodium atom. No, no, a sodium atom cannot hydrogen bond. We just looked at the conditions for that, so I'm going to say no to that. What about this here? We have a carboxylic acid. You don't need to know the type here of compound, but you need to notice that we have this OH group. So the way that this would look if we drew the Lewis structure, we have this CO double bonded up here, and then we have an OH group. So this is the portion that can hydrogen bond. So I'm going to say yes for compound 2. Compound 3, excuse me, is just a nonpolar. It's ethane. So we would have 2 carbons in the middle, 3 hydrogens kind of evenly distributed here. It'll take me an hour to draw them all. But we have ethane here, so we know it's nonpolar. Definitely no OH, NH bond, so we're going to say no to hydrogen bonding. But lo and behold, we have compound 4 here. This is methylamine, right? So 1 carbon's methyl. We have a nitrogen. We call it an amine. But again, you don't need to know the nomenclature, but you do need to know that there's going to be at least 1 NH bond here. So hydrogen bonding is possible with molecules of 2 or 4. All right. Hydrogen bonding. All right, so I'm looking for anything with an OH bond. So I instantly see water here. I know water, ammonia. Those are very common when we talk about hydrogen bonding. Strongest intermolecular interactions with ethyl alcohol. So here's the structure. We can see it can hydrogen bond. So I'm going to grab hydrogen bonding right off the bat here. I'm not even going to look at the other interactions because I'm looking for intermolecular here, and that's definitely the strongest. Ammonia. So once again, hydrogen bonding is the answer. Whenever you have a liquid or even a solid with a covalent compound with an unusually high melting point compared to an ionic compound, which are always higher melting points, it's usually due to hydrogen bonding. London forces are dispersion forces. 26 here. So we have these helium atoms that are just kind of by themselves here, right? So we have just helium, noble gas. It's too noble. It doesn't want to interact. It doesn't want to react with anybody. We know this doesn't happen. We don't see, here's a side joke, right? We don't see hee hee. We don't see this diatomic molecule form. But they do attract each other. So I'm going to try to draw these lines of attraction here. And these are going to be representative of the dispersion forces. So remember everything nonpolar, even monoatomic atoms like helium here, they all have those dispersion forces. So 26 is A. Let's look at 27 here. Entirely due to dispersion forces. So I'm looking for something that's non-polar here, right? So if I only have dispersion forces, I need a non-polar molecule. So I see here this structure would be like ROR here. We have these methyl groups with an oxygen in the middle. If I drew this Lewis structure, I would see that I definitely have a polar molecule. So I'm going to eliminate this compound E here. D is an ionic compound. So anything that's ionic, we're going to cancel that out. We just looked at hydrogen sulfide a short while ago, so we know that that's going to be polar. And then A, if we were considering A, this would end up being like a radical with a resonance structure that results in a radical. I mean, I have like an odd number of electrons. So nitrogen would have one unpaired electron. We would do two resonance structures like this, but both would be polar. So we would eliminate A, and then our only non-polar compound here is the ethane, C2H6 that we saw earlier. So to confirm, if you drew the Lewis structure, you would know that it's definitely non-polar. So again, when you're making your choices here, if you're looking for something that's only exhibiting dispersion, London dispersion forces, it has to be non-polar. Because as soon as it's polar, then it would have a dipole-dipole interaction. And then if it can hydrogen bond, we know that's the extreme dipole. So let's look at 28 here. We have now some information about temperature, but we really don't need that for calculation or anything. We're just told that once we get to 27 Kelvin, neon would start to go from a gas to a liquid. It will condense. And we know neon's a noble gas. It's not polar. So this is another way of saying London dispersion forces must be what's causing this to condense. 29, ion dipole. So I need an ion, I need a polar molecule. These are both ions, these are both polar, these are both ions, these are both ions. So my only option that has an ion with a polar molecule is sodium ions in water. Right, so I need one of each, an ion and a dipole for ion dipole interactions. All right, 30, highest boiling point. So we're looking for the highest intermolecular forces, the higher interactions. In this case, it looks like everything's pretty consistent. We have a carbon as our central atom, surrounded by four other atoms. So we have bromine, hydrogen, fluorine, iodine, chlorine here. So that's really the only deciding factor here will be the molecular weight, the molar mass of these compounds. So what I would do to shortcut this, since they're all the same, they all have four of the same atom and then carbon. So we know they're going to be equal as far as mass for carbon. So I would just look at this other atom. Iodine is the heaviest. On the periodic table, iodine's 126.9, so almost 127 grams per mole per iodine. So D here, this is over like 520 grams per mole for each of these molecules. So this would definitely be the heaviest, and this would have the highest boiling point because of more molecular interaction because of that molar mass. So remember how long the molecule is, the surface area can interact, or can affect the amount of intermolecular interactions. So how big your molecule is versus, or long versus rounded, so shape, and then also molar mass. The heavier mass, the more intermolecular interactions, the higher boiling point. All right, we'll do 31, and then I'll go down to some of the last chapter material for the rest of the time. So we have here within these pairs, we want to choose the higher boiling point. So group one, I have water or an ionic compound. So potassium iodide, I know is an ionic compound. It would be a solid at room temperature. It's definitely going to have a higher boiling point. Next, I have HF versus HI. So HF, hydrogen fluoride, can hydrogen bond. Hydrogen iodide cannot. So I have HF in this group of two. And then my last scenario, I would check molar mass. So chlorine is above bromine on the periodic table. So bromine is heavier. So that would have a higher boiling point. So we see that A would be the winner here. That lists all of the pair, whichever of the two has the higher boiling point. These are just definitions here. So while we're here, 32, we're looking at this measure. So here's my surface of water. We're kind of pushing down like we're that bug, that surface skipper bug. So we talked about surface tension being that elastic force in the surface of a liquid. The attractive force involved in capillary action. This one's cohesion, right? When we have like molecules, they are cohesive. And then unlike molecules, they adhere or they're adhesive, like a tape sticking on something, right? An adhesive property. But for like molecules, they're cohesion or cohesive forces. All right. So let's see here. Where's our next topic? Here we go. So 36 and beyond. This is dealing with like phase change and things of that nature. All right. So we looked at our phase diagrams and how when we are not phase diagrams, we're looking at where we added heat and we changed from a solid to a liquid, and then we saw this isothermal process where we were doing our actual phase change where all the energy went in to change from a solid to liquid or vice versa. Sorry, my 2-year-old wanted to join the session. So what we have here is we're given a mass. We're given our heat of fusion, which, if you recall, is the amount of energy that would be required to melt something from so going from solid to liquid state. And this gives us the quantity in moles. So what I need to do here is find out how many moles do I have of my iron. So if I have 2,000 grams, right, 2 kilograms, I could divide this by my molar mass of iron. So I go to my periodic table. I see that's about 55.85. 55.85 grams per mole. So I'm going to divide my 2,000 by 55, and I see that I have about 35.8 or so moles. So 35.8 moles. All right, that's not going to get any better. All right, so if I use this 35.8 moles and I multiply by 13, that should give me the amount of heat needed to melt this much iron. So 13.8 times 35.8, I get 494. Oh, and lucky for us, that is an answered choice. So again, we are melting, so all of our heat is going into that phase change. So we don't have a temperature change here. Notice we don't have an initial and a final temperature. So we use just that simple equation where it's the delta H times the number of moles. All right, for 37, now we're going to have three different steps here that we would have to calculate. So something like 37, this is probably one of the most time-consuming and challenging questions that you may see. So I'll walk us through some of the details here. We're given a normal boiling point of our compound. So that means at negative 33.3 degrees Celsius, we're going from a liquid to a gas. And we're told here that we start off with this 25 grams of ammonia liquid, and we're at a starting temperature of negative 65 C, and our final temperature at the end of our evaluation here, at the end of our phase change, or the end of our process really, will be negative 12 degrees Celsius. So let's see. How we can break this down and figure out how much energy we would need to go from liquid at negative 65, and we're going to be in gaseous phase at negative 12 by the end of our consideration here. So I'm going to work down here just for space. So I mentioned that we're going to have three different kind of phases in our calculation here. So our first step would be to warm up our liquid. So we have our 25 grams of liquid at negative 65 C. We're going to get this to its boiling point here. So I'm going to take my 25 grams, and this equation will be the Q, right? Oh, 25, that's supposed to be a G. This Q, usually we write it as a lowercase q. So 25 grams, so MC will be the specific heat for my liquid phase here. So that's going to be the 4.7 joules per gram Celsius. So I have 25, so my M, my C, and then my delta T. So this is where I have to be careful. I'm going from my final temperature is negative, let's see, maybe I can write it down here. My final temperature would be negative 33.4. Because I'm right above my boiling point, or right below rather my boiling point, and my final temperature, or I'm sorry, my initial temperature was negative 65. So what happens here, we have negative 33.4, which is right before we enter into that gas phase. We're still at the highest temperature for our liquid. So this is my final temperature here for this phase change, or this warming up of liquid. And then I subtract my initial temperature, which is a negative value. So I end up doing negative 33 plus 65. So my delta T here would be positive 31.6. So let me go to a whiteboard real quick here to do this, because it's getting messy. All right. So again, we're just heating up or warming our liquid in this first step. So we have Q equals MC delta T, and we had 25 grams. My specific heat capacity for my liquid phase was 4.7 joules per gram Celsius. And then we see our delta T, that was from the negative 65 was our initial. The final would be the negative 33.4, because we didn't quite change to a gas yet. And that was the 31.6. So we multiply all these together and we should get 3,713 joules. So now we're about to do our phase change, right? We've warmed up our liquid. We're about to turn from liquid to gas. So now in our second step here, we're going to take, we're going to find based on how many moles we have, and then times the heat of vaporization, right? So how many moles, we can find that from 25 grams. Let's go back real quick here. Right, we saw two different equations when we did these phase change calculations, right? We saw the one where we have a temperature change, and then this second equation, when we don't have a temperature change, we know we're changing the phase. We just use delta H times moles. So I have 23.3 is my molar heat of vaporization. That implies 23.3 kilojoules per mole. So I would multiply that 23.3 times however many moles I have. And that would be the molar mass of ammonia divided into 25 grams. So I would do 25 divided by 17. I have about 1.47 moles. So I do 23 times 1.47. And this, remember, this would require more heat than just heating up our liquid. Actually doing this phase change, we would find we need to put in 34.25 kilojoules. So I'm gonna write that off to the side here. So we have 35.25 kilojoules, plus if we convert it, our previous answer, it would be about 3.7 kilojoules. And now we are about to heat up our gas now beyond our phase change. So this would be our last set of Q calculation here. Let me go to another whiteboard. All right, so we've done our warming up the liquid, we've done our phase change, delta H calculation. Now I'm going to do one last Q calculation. So I still have 25 grams of ammonia. My um, my specific heat now in the gaseous phase, if you look back at the practice test, it's less. It's only 2.2 joules per gram Celsius, right? This is my C value in gas phase. This was my M. My delta T now, we're going up to -12. So that's going to be my final temperature. And I started now at the highest temperature for my liquid phase or my lowest temperature for gas phase. That was that negative 33.4 right before we became a gas. So -12 plus 33, I'm going to have a delta T here of 21. Oh, I can't see. 21.4 is my delta T. So I multiplied 25 times 2.2 times 21. So the heat needed here would be 1,700, 1,000, sorry, 1,177 joules. So we're going to add 1.7 kilojoules plus the other two values together. We had 3.7 in our first value, and then we had about 34 for our second during that phase change. So when you add 34 plus 3.7 plus 1.7, I promise we'll see an answer close to that. So I'm going to go back to the exam here. Right, so I added my three different amounts of heat, and collectively we should be around 39.1. This 34.5, that was only during the phase change. So don't forget that we have to heat up the liquid in step one, and then in the third step of the heat calculation, we had to heat up our gas. So again, the largest energy is with the phase change, that 34.5, where we did the moles times our 23.3, our heat of vaporization. But we still have to add those other two, heating up the liquid and then heating up the gas. All right, so that will be like the longest type of calculation that you're going to see on your test. There may be like one of those. All right, so I'm going to delete this a little bit here so I can see the next question. But if you have any questions about that, please let me know. We'll look at rest of the time here. I'll do as many phase diagrams and things as we can. So if you recall, this is my triple point here, where I have all three phases of matter present at one time in like this equilibrium state. So I have solid, liquid, and gas at A. That's my triple point, but that's not what B is. We're asked about B here. If you remember B, this is the critical point where we could have a supercritical fluid it's kind of like between a liquid and a gas here at point B. Where the pressure is high enough that it wants to be a liquid, the temperature is high enough, it wants to be a gas. So at point B, we get where is it? The critical point. There we go. So answer choice D here, where we would have, oh, that didn't really do it. Answer choice D. Let's see here. So know how to graphically interpret these phase diagrams. Like here, for example, we know that at the highest pressure and lowest temperature, we would have a solid. Somewhere in the middle, we would have a liquid. And then at high temperature, low pressure down here, we have a gas. So if we look at normal atmospheric pressure here, 1 atm, 760 torr, point F here, this would be in the gaseous phase. Just because it's above the dotted line doesn't mean that it's not in this phase. So point F here, we would say is vapor. Vapor is another way of saying gas. It's not on that border, not on that line. So we wouldn't say that it's vapor and liquid. But if the point was like, oh, it's not letting me draw. But if it was on that actual phase line, then we would see both vapor and liquid. But since it's only in the gaseous section, we would say just vapor. You might also be given phase changes represented by these diagrams here. So we're looking specifically for vaporization. So let's think about that. Vaporization is the phase change from liquid to gas, right? So if we're going from liquid to gas, if we kind of identify our regions here, we can see that this would be liquid to solid in this first one. So this would be freezing. So that's out. Next I have from solid to liquid. This will be melting fusion. So I'm gonna skip B, right? We're looking for liquid to gas here. This is gas to liquid, right? We go from down here to up here. So gas to liquid, this would be a condensation. This is the opposite. We'll get there. Let's see, part D. Now we're going directly from solid to gas. So this is when something sublimes, right? This is sublimation. So E must be the right answer by process of elimination. We're in the liquid phase. We're going to the gas phase here. So we must be in vaporizing, right? So that's our correct phase change.
I noticed the regions on like the practices here, they aren't labeled.
Mhm,
Are the regions the same every time?
mhm. Correct, yes.
Okay,
So
thank you.
whenever you have low pressure and low temperature, you're going to have a solid. Whenever you're in the middle, it's going to be a liquid. And then when you have high temperature, low pressure, you would be a gas. Um, so you can the lines might shift a little, like the what's the word I'm looking for? Like the axes, right? The angle of how they're presented, but still the same regions. So what's a solution? It's a homogeneous mixture, right? It could be gaseous phase. Rarely do we say that we have solid solutions, but there are some alloys that kind of fall into that description. But the best description of a solution is a homogeneous mixture of two or more substances. So whenever you're considering, is this the best answer? Look for the best, the closest match, the definition that can't really be wrong in any scenario. Um, all right. So what's the largest proportion in a solution? It's not the solute, right? It's not the solute. It's our solvent. Uh, let's see, which is not soluble in water. All right. So we know that water is polar, right? HOH here. Oh, okay. So I have my polar molecule. So I'm looking for something that's non-polar. So this is an alcohol that's polar, that's ionic. Ammonia, that's definitely polar. So now I'm down to some vitamins that I know if you looked at worksheets, you would have seen these. You'll know that vitamin E is non-polar. And then vitamin C, you can think about this being very water soluble. It has a lot of these OH groups in vitamin C. So it would be water soluble versus vitamin E is a fat soluble vitamin. So this would be something that you would just have picked up during lecture or during the videos. Number 44, we can look at the structure here. So we want to know what's most soluble in this carbon tetrachloride. All right, it'll take me an hour to draw it here, but we'll see that this is well, Cl. It's supposed to be Cl. It'll be a non-polar molecule, right? Carbon in the middle, four equal bonds. So what's most soluble? The other non-polar compound. Sodium hydroxide's ionic, water's polar, ionic for B, and then A is also polar. So when we want to know what's most soluble in something else, we want to think about like dissolves like. So we have nonpolar molecule, carbon tetrachloride, octane, CH18 would be most soluble. All right, let's do at least one of these here, and then I'll pause for a second. So let's do 45 together. So 45, we're asked here to calculate molarity. So this is towards the end of our chapter here. Um, let's see here. How about we do, let's see. So 45, we're given the fact that we have 78.6 grams of potassium fluoride, and we want to produce 225 milliliters of solution. So first we need to get moles. Oh, moles of KF. So that's going to be 78.6 divided by, if I add together potassium and fluorine, I should get about 58 grams per mole. So I'm going to do 78 divided by molar mass, and I get about 1.35 and some more decimals moles of potassium fluoride. I'm going to divide by liters. So 0.225 liters. I convert it milliliters by dividing by 1,000. And then 1 divided by 0.2, I'm going to get about a 6.01 mole per liter or molar solution. All right, so let me stop share for a second here. Let me actually, I'm going to stop recording. Where's my recording button here?